Okay. So we're looking at this graph of f of x, and it asks us to sketch the tangent line at x equals 3. So we're just going to sketch in a tangent line right here. And that's really about all we know. Okay, it's just a sketch. Would we say that the rate of change at 3 is positive or negative? It's negative, right, because it has a negative slope. So then they tell me the equation of the line tangent to f at x equals 3 is this equation, y minus 1 equals negative 1.75 times x minus 3. If it's okay with y'all, I'm going to rewrite that as y equals negative 1.75 x minus 3 plus 1, just because that's how I'm used to seeing it. Okay? So what information do we get from this line about the graph of f? So what all does this equation tell me? Okay, it tells me the instantaneous rate of change, which is the slope of the tangent at x equals 3, and that's that value, negative 1.75. Anything else it tells me? There's two more numbers up there. What do they represent? Yeah, or we could just say it's a point. It's a point on that line, right? It's a point on the line. So the point 3, 1 is on the graph of f. Okay, now we could tell that just from looking at the graph, but right. Now, because my instantaneous rate of change at 3 is negative 1.75, we could also say that f prime at 3 is negative 1.75. They're all the same thing, all right? All those same things, okay? Now, we don't have enough information to find f of 3.1, all right, because that would be hard to do looking at that graph, but could we estimate it, all right? So that's our next step. Can we take this line and estimate it? So, do you think f at 3.1 will be greater or less than f at 3? All right, because 3.1 would be like, let me use a different color. All right, it would be right here. Okay, so do you think that value is going to be greater or less than the value of at 3? It's less, okay? How do we know that? Yeah, I mean, we can just look at the function itself. What's the function doing at 3 from 3 to 3.1? Is it increasing or decreasing? It's decreasing. So it would be less because f is decreasing. Okay, so we don't even have to really know the derivative there. We can look at the function and know that. Okay, so it tells me to approximate f at 3.1 by plugging in 3.1 into our tangent equation. So f at 3.1, we're going to approximate by plugging it in. So negative 1.7 times 3.1 minus 3 plus 1. All right, and you should get what value? 0.825, okay? So this is the tangent line approximation. Okay. So we use the tangent line to approximate the value of the function, all right? 0.1, 3.1, that's pretty close to 3, so we could use that to make an approximation. Is our approximation an over or an underestimate? What do you think? That 0.825, is it an over or an underestimate? What do you think? Because remember, this value is coming from the line, not the curve. It's an under. Why is it an underestimate? Yeah, and the slope's, and that line's below my curve, right? So it would be an under approximation because our tangent line is below our curve. Okay. All right, cool. Let's look at the next 3 questions. Right. So now it says, for what values of x do you think that the tangent line at x equals 3 will do a good job of approximating the function value? Okay, so what values of x on our function could be covered pretty nicely by that tangent line written at 3? And you don't have to have exact values there. It can just be a general set of values. Okay? Well, would it be a good approximation at 2? Would the tangent line approximate the values of the function at 2 very well? No. Would it approximate the values of the function at 6 very well? No. In fact, that line has a totally different slope. That tangent line would. So we would have to pick values that are very close to 3. Right? So we'd want to pick values that are very close to 3 because that's close to the function. And by it, I mean the tangent line. So I'll put tangent line right there. Okay, because it's close to the function. We want to choose values where the tangent line is close to the function. If we get out to 2 or over here at 6, that tangent line is not going to be close to my function. All right. So now what we want to do is let's go back and look. All right. We want to pick an x value on the graph where the tangent line would give us an overestimate of the true function. All right. So we want to pick an x value where if I drew a tangent line, it would give me an overestimate of the actual function value. All right. What do you think? There's lots of right answers here. Any ideas where our tangent line would give me an over approximation? Yeah, 0 is a good one. All right, at 0, okay. If I draw the tangent line there, where is my curve, above or below? Where's my tangent line? Sorry. It's above the curve, right? The tangent line is above the curve. So, tangent line above the curve equals an over approximation. Okay, so x equals 0 would be a good choice. All right, then it says, all right, give me one where it would be an under approximation. Okay, x equals 2. Okay, if I do my tangent line there, yep, it's below the curve. Okay, my tangent line is below the curve. So it equals under. We could even go over here and say it like 5. All right, that would definitely be below the curve again, right? So there's lots of places in there, okay? Now, I want you to look at the graph. We talked about this in pre-cal before we actually knew what some of these words meant, all right? What feature of my function is causing that tangent line to be over or under? When it's concave up or concave down, okay? When it's concave down, then my line is above the curve, so it's an overestimate. When it's concave up, it holds water. It's an underestimate. It's below the curve. And that's the main thing we want to talk about in terms of approximations, okay? So on the first one, we said x equals 0. And the reason that is true is because the graph is concave down. Right? Another one we said was x equals 2 or x equals 5, and that's because the graph is concave up. Okay, so when we're concave down, the tangent line would be over, so it would be an over approximation. When we're concave up, the tangent line would be under the curve, so it's an under approximation. And that's literally what I do. Like, I'll check the concavity, and then I think about what the line would look like. All right? It's not necessarily something that I memorize. Okay? All right. So now let's look at number 7. Okay? It says, given that f of 1 is equal to 4.5, and f prime at 1 is negative 0.75, let's approximate the value of the function at 0.99. Well, to approximate, I need a tangent equation. All right, so let's write the equation of my tangent line. To write the equation of a tangent, I need a slope and a point. Do I have that? Yeah, okay. Here's my slope. Here's my point. Okay, so my tangent line would be y equals negative 0.75 x minus 1 plus 4.5. Okay? To approximate f at 0.99, we're literally going to plug 0.99 into that equation we just had. So negative 0.75, 0.99 minus 1 plus 4.5. Okay, and what'd you get? Yep, 4.508. Now, think about this. You can always kind of double check to see if your math is correct, okay? We knew that at f equals 1, the y value was 4.5. I'm doing f at 0.99. It should be close to 4.5, is it? Yeah, okay? So we know we did it right. It's one of those things you can kind of check the reasonableness of your answer. If you got 27.4, we did something wrong, okay? Like, it should be obvious to us, glaringly obvious that we did something wrong, okay? So, remember how I said at the beginning of calculus we would only do about 4 things but call it 19 different things? This is one of those cases, all right? Linearization is just the equation of the tangent line. Okay, that's all a linearization is. And so that's just another vocab term to say, hey, give me the equation of the tangent line. The nice thing is we're going to use it to approximate values of the function, all right, that might otherwise be difficult to ascertain. Okay. And so if we look at just in general terms, okay, if we were going to write the equation of this tangent line, so we have f of x, and we're doing the tangent at the point a comma f of a, okay? We know that we need, hold on a minute, I got crazy things on. We know we need a slope and a point, okay? So what's my slope going to be at that point? X prime, and it's at A. Yep, so we're doing the point A. My ordered pair, we're just writing this in general terms, is A, F at A. Okay? So when I write my tangent equation, it's going to equal my slope, F prime at A, times X minus my X value, which was A, plus my Y value, which was F at A. Okay? Now, the only thing we're going to do when we talk about linearization is we're going to change y to L of x. It is still just the equation of your tangent line. Okay, so it's just the equation of your tangent line. So you'll see it referenced as L of x. That's because they call it a linearization, but it's just your tangent line. All right. Now, why they call it a linearization is that all functions are locally linear. Meaning, if I zoom in on any function really, really close, okay, and I get, x is a 100th above and a 100th below, that piece of the curve will look like a line. That's what that means. So if we get really, really close, all right, around certain values on a curve, it will look like a line. All right, so if we zoomed in, and we could do that on our calculator, but I think you trust me at this point, that would make sense. Otherwise, a tangent line wouldn't work, okay? That if we get really close, all right, it gives me a linear-looking function, all right? And then we use the linearization and it makes us sound really smart, to approximate values of the function. That are close to the point of tangency. Okay. And the main reason we might want to do that is because it replaces something that could be difficult, a quadratic, a cubic, a rational function, with a linear function, which is much easier to work with, all right, in terms of finding values. Okay. So I want to show you how we use these problems, what they're going to ask me in terms of how it will show up on your AP test. Okay, and just show you some different things. All right, and all the different ways AP likes to assess you, tables, graphs, the whole 9 yards. Oh, goodness. You have mail. Yeah, when we're done. You will or won't? Oh, okay.
No.
Okay. Oh, my
I'm
hips.
not losing my leg. I already lost my leg.
All right, so let's look at what we got here. Okay, so here's the first one. Find the linearization of f of x equal to the square root of 1 plus x at x equals 0. In other words, write the equation of the tangent line, okay, which we should be able to do. Go. All right, so write the equation of that tangent line. I want you to find the linearization. Think about what you need and what you need to do. That's something we've already been working on. Don't quit playing. Get your new sassy haircut over there playing all the time.
Saying when x equals the square root of 1.02.
Yes. Oh, no, actually, it's not 1.02 because what's under the original function already? So if it's the square root of 1.02, I've already got a 1 under there, so what would x be? 0.02, yeah, or 0.2, whatever it is. We'll get to that part in just a second. Okay, the second part of that question. So to find the linearization, all right, do your derivative. So f prime at x, it's a chain rule, but it's an easy chain. All right, and then plug in 0. Okay, so to get 1/2. Then so that's my slope, and I need my ordered pair. So I'll plug in 0 to the original function, which would give me 1. So now when I write my tangent equation, 1/2 x minus 0 plus 1. Okay, so that's my linearization. How'd you do on that? Okay, so we should be good on that. Now, the next part is to approximate this value, square root of 1.02. Well, what we have to remember is that f of x is the square root of 1 plus an x value. And if I want to evaluate so that I have the square root of 1.02, what x value would I actually be plugging in? 0.02. Okay, so the x value I'd actually be plugging in is 0.02, so that's weird. All right, so f at 0.02 we say is approximately my linearization at 0.02. So 1/2 times 0.02 plus 1. Okay. Should give us 1.01. So, question about that process. Not so terrible? No, much better than related rates. Yeah, I agree. I concur. Okay. All right, try the next one. And we'll talk about the second part of that in just a minute. Okay, so try the first one. Can you write the linearization? And then we're going to talk about the accuracy of the approximation. All right, did you get your linearization? All right. All right, you could leave the 0 off at the if you wanted to, okay? But you could, or leave it, they don't care, right? Because they don't expect you to simplify. That shows you know what you're doing. So now what it's asking us is how accurate is the approximation? So L at 0.1 to F at A plus 0.1. In other words, I'm plugging in an extra 0.1 into, or adding a 0.1 to the x value I plugged in. So the x value that I'm considering is L at pi over 2 plus 0.1. Okay, so that's what it's saying. That's what it wants you to find. Okay, L at pi over 2 plus 1 will approximate F at pi over 2 plus 0.1. And we're just going to put that into that linearization. Now, the nice thing is, it's pretty easy, right? What happens to your pi over 2s? They would cancel out, so I would just get a negative 0.1. Now it says, use your calculator. What is the actual value at pi of the function f at pi over 2 plus 0.1? So what is cosine at pi over 2 plus 0.1? All right, so that I would put on my calculator. That's what I got, negative 0.099833. So it's pretty darn close. All right. How accurate? Pretty darn accurate. All right. Differs by, what, 1,000th? Because if we rounded, it would give me that 0.1. Yeah, so pretty darn close. All right. They will not ask you to give that error in terms of how different they are. They won't ask you that. Okay. All right, so let's look at a table. You know, it wouldn't be AP if we didn't put a table on there, right? We got to do a table for fun, just to keep us, honest. And it says selected values of a differentiable function and its derivative are given in the table. Write the equation of the tangent line to the graph at x equals 4. All right. Then use that tangent line to approximate the function at 3.8. So that's a value I don't have in the table. Take a second and do that one. Using your table, write the equation of your tangent line.
Last question that we did.
Mm-hmm.
So on the AP exam, are we supposed to put like the whole number? Like,
No, they're not going to ask. You'll always round to 3 decimal places unless they tell you otherwise. Okay? But they probably won't ask this question on the AP test, this part. All right? They might ask you to approximate, but they won't ask you to tell the difference between the two. And that's what this was for. They differ by 1,000.
thank you.
You're welcome. All right, so let's pick out what we need out of this table. We're writing the equation of the tangent line at x equals 4. So this is the column that I need. What's my slope at 4? 6. My x value is 4. And then what's my y value at 4? -5, okay? So that's my equation, right? That's my equation. So now we want to approximate, all right? F at 3.8 is approximately L at 3.8. So 6 times 3.8 minus 4 minus 5. And what do we get for that? Negative 6.2. There you go. Okay. Not too terrible, all right? Just using that tangent line to make an approximation, all right? The only other thing that they would add to that table question would have something to do with, is it an over or an under approximation, all right? So let's organize those concepts really quick, and then we're going to be good to go, okay? It all revolves around concavity, okay? So if we look at this first example, how would you describe its concavity? It's concave down at the point that it's talking about, right? So if our function, if f of x is concave down, okay, that means f prime, the derivative, is decreasing. It means that our derivative is less than 0, and we have an overestimate. Okay, our entire next unit is all about how the graphs of the function, the derivatives, and like the first derivative and second derivative all relate together in the information it tells me. Okay, so there's a lot more of this stuff coming up. Okay. If we look at the second one, how would you describe this one's concavity at point B? It's concave up, okay? So don't write with a highlighter. When f of x is concave up, means our derivative is increasing, which means our derivative is positive, we're going to get an underestimate. Okay. I remember that just by looking at the picture. Where would the tangent line fall, above or below? Okay, so if I know the concavity, it'll tell me which way it's going. All right. Okay. All right, here we go. So key takeaways and one last example. All right. Yay! What feels like a normal lesson when you don't want to shoot yourself in the face. Okay. Stop. Gosh, Rick. Oh. All right. So let's look at these first two. All right. The tangent line approximation at x equals 3. All right. So here's x equals 3. Over or underestimate? Over. Okay. We got something that's concave down. That line is above the curve. It's an overestimate. Right? What about the second one? At x equals 3. It'd be an underestimate. It is under the curve, so it would be an underestimate. Okay? So this table right here is just important. It gives you a lot of information in terms of justifying, all right, something to be true, all right? So our slopes, okay, are increasing. If f prime is positive, that means my tangent line is an underestimate. That's because it is concave up, okay, and so forth. All right, so it's just an organizational table of everything we just said, okay? All right, here we go. Let's look at this one, all right? So this one's more like what we might see on the AP exam, especially in a free response, okay? For a twice differentiable function g of x, that's important, okay? How many derivatives does that mean I can take? I can take 2, all right? I can take 2 derivatives. And if it's differentiable, that means it's also what? Starts with a C. Continuous, yes. If it's differentiable, then it's continuous, okay? So here's the things that it tells me. We're going to need this. G at 2 is equal to 7. Okay, g prime at 2 is negative 3, and g double prime at 2 is negative 5. Okay, so it's giving me 2 values right here, all right, and what they're going to mean to me. All right, so here we go. All right, notice in this table, the second column says f double prime. All right, f double prime. If f double prime is positive, that means I'm concave up. If f double prime is negative, that means I'm concave down, okay? So that column is going to be really important to us in this case, all right, because it's going to help me to know some things, all right? Step 1, use the tangent line of g of x at x equals 2 to approximate the value of the function at 2.1. Go. Okay. What's your tangent equation or your linearization equation going to be? Yep. Yep. Plus 7. Did you get it, Wilmer?
Yeah, I got it.
I know, you're anti-tangent lines, so I'm glad you got that one. Okay. So you're kind of the Debbie Downer over there. You kind of hate everything, Roderick. It's okay. You got the hater rate. The hater rate is strong in you today. All right. So now we're going to do our linearization at 2.1 to approximate g at 2.1. And we're just going to plug it in. All right. So which would be negative 3 times 2.1 minus 2 plus 7. And so that would give me 6.7. Okay, so that's part 1 of that question. All right. Did you get that part?
I didn't get that part. I only put the
Oh, you only put, okay, you gotta pay attention. Yeah, gotta read. All right, so now let's look at part B. Okay, this is where it asks me, is the approximation in part A an overestimate or an underestimate of G at 2.1? And the thing is, we've got to rely on what we're given. Okay, what we're given is this piece right here. All right, I didn't need it to write the linearization, so I must need it for something else. Okay. G double prime is -5. That means that G is concave up or concave down? Concave down. And so my linearization would be above. So it's what kind of approximation? It's an over. Okay? So here's what we have to say. It is an overestimate. All right? Because. All right? Now, we can't justify using things I was not told. Okay? Did this problem say anything about concavity? No. Okay? The reason it's an overestimate is because they told me G double prime at 2 is negative. Okay? Now, after you say that, if you wanted to go on to say, okay, you don't have to, you can stop right there, but this part could be added, which implies G of x is concave down at x equals 2, okay? You do not have to put that part in pink, all right? The justification is that second derivative is negative because that's what they gave me, okay? So you can't put words into the problem's mouth. We're going to run into that a lot in the next unit, okay? Where we have to justify based on what I'm given, okay? Make sense? All right, yay. We like that lesson a little better, everybody but Roderick. Okay, so there was a worksheet back there, and if you looked at the top of it, there were a couple of problems out of your text, 3, 5, and 7. Okay, that would be good ones to look at. And then worksheet 5.5. Those all came from AP Classroom. All right, so they would be some good practice. All right, and you probably shouldn't have a lot of questions about these, right? Because this is something we've been doing. So again, just look at the questions, be sure you understand what they're asking. You could do the justification, all right? Probably don't need as much practice on this as we did other things, okay? All right, you do have a wrap up today on Google Classroom. Let's get that done so I can give you a point today.